So are you able to see my screen now?
Yes, sir.
Yes, yes, sir.
Okay, okay, fine. Thank you. So in the first part of the lecture, my idea was to give an idea of what an ocean general circulation model is. So you might have seen that it's a very set of equations that is to be solved, a numerically set of equations which is to be solved on a computer. Now, the good thing now, particularly for you and those who are interested in ocean model, is that it's all been done. We don't have to write those equations or solve them. And so such models are readily available. And because those models are readily available, the ocean modeling has acquired quite a bit of popularity in terms of its applications. So once you have an idea on what to do with the model, it's possible to download the model, install it, and set it up in your computer, make changes to it, and do the experiments that you do so that you can learn about oceanography, about ocean processes, like the question which somebody asked just now, biological impact on oceans, and so on. So in this 1 hour, what I plan to do is to show you some examples of ocean general circulation applications of ocean general circulation models, which has been done by students in the center. So I'm going to use one model that is called the Ocean General Circulation Model, developed at the GFTL Princeton. That's called Modular Ocean Model. So it was called Model Ocean Model because different pieces, different parts of the equations were initially designed as different modules. So this model is a very good model. It's been evolving since 1960s, and it's very widely applied. So I would like to show you some examples on how this is applied. Now, our applications for the Indian Ocean. So I think a bit of an introduction about the Indian Ocean is in place. So the larger oceans are Pacific and Atlantic, which has been very well studied by Europeans, Americans, and so on. But compared to that, Indian Ocean is small, and Indian Ocean has another speciality that its northern boundary is kind of close. That means the Atlantic and Pacific are connected to the polar region by the oceans itself, whereas Indian Ocean we have a land boundary here. And because of this peculiar geographic setting, we have the monsoon climate with 4 months of rain from June to September, and then we have a northeast monsoon which is running right now from November to February. So that is manifested in these winds. So this is the climatological, that means long-term mean winds that we see that in July, the winds blow from the ocean towards India with a very, very strong winds in the Western Arabian Sea. This is Arabian Sea and this is Bay of Bengal. So on the western side, the winds are very strong. And these winds blow from May to almost till early October, and they reverse to become northeasterly. In January, for example, the winds are weaker and they blow in from the land to the ocean. Now, because the oceans are driven by wind, this forcing function is continuously on transition. It is evolving all the time. It is time dependent. So in January it is like this, and then it slowly would weaken, and then it would reverse. So the ocean would be dragged along. So the ocean also responds to this, and ocean circulation changes, ocean temperature changes, ocean salinity changes, and so on. So this is an example of how that ocean temperature is changing as a function of season, right? So the Indian Ocean is fairly warm, with the temperature exceeding 28 degrees in large region. So this is a picture for July, where you can see that most of the Arabian Sea and the entire Bay of Bengal is very warm. The western side of the Arabian Sea is cool. Okay, so the eastern side of the ocean is warm and the western side of the ocean is cool. Now this pattern changes from an east-west orientation in summer to a north-south orientation in winter. In winter, the northern side is cooler, whereas the southern side is warmer. So this seasonal change is very distinct in the Indian Ocean because of our monsoon climate. And this is a picture of the rainfall. So we have very large amount of rainfall in the Bay of Bengal and also along the near the western side, west coast of India, and our land. Whereas in January it is mostly dry. Now, this rainfall has a large asymmetry in terms of these two basins, right? This is Arabian Sea and this is Bay of Bengal. Most of the rainfall is falling on the eastern side, and also all the main rivers are discharging into the Bay of Bengal. Consequently, the salinity of the Bay of Bengal is very low, and the salinity of the Arabian Sea is very high. So, this is another distinct seasonal feature of the Arabian Sea. So, given that background, this is the configuration of the model that we are applying. This is the GFTL model version model, and the version that we have used is version 4 by the students who have done their PhDs. And this is configured for the entire tropical Indian Ocean, extending from 30 south to 30 north and 30 east to 120 east. Now, the horizontal resolution that we have chosen is a quarter degree, that is approximately 25 kilometers, and there are 40 vertical levels, and with a resolution of about 5 meters in the top 60 meters. Now, this resolution is decided based on the mixed layer that we would like to resolve. So, in the Arabian Sea, the mixed layer depth is about 100 meters, whereas when we come to the Bay of Bengal, it is 10 meters or less. So, this is sufficient for large regions, but it's not the best for the northern part of the Bay of Bengal. Now, this model is forced by satellite data of wind stress and wind speed, and then other parameters coming from reanalysis systems like air temperature, humidity. Air temperature and humidity, shortwave, incoming shortwave and longwave radiation enters directly into the model, and it needs to calculate sensible and latent heat fluxes based on the other parameters like temperature and humidity. So it also has rainfall entering as a force as well as river discharge. Now, the problem that I'm going to show today are listed here. One of them is the so-called Arabian Sea mini whirlpool, which is a seasonal phenomenon. And then the Indian Ocean dipole, which is an interannual phenomenon. There is a Bay of Bengal freshwater effects, which is a physics problem. And it has two other component problems like Eastern Arabian Sea rainfall and global runoff. Now, I must say that in 1 hour, it's not possible to cover the whole thing. But I don't want to cover the whole thing, and rather than I would explain one of them in as much detail so that you understand the problem fully. So I would cover as much as I can, but my expectation is that I would be able to cover the first two. Okay. Right. Now, what is warm pool? The large stretches of tropical ocean is warmer, and there are some regions which is warmer than others. And such regions are called warm pool. So there is also a very nice definition of warm pool. The warm pool in the tropical ocean is defined as the region where the temperature, sea surface temperature, exceeds by a value of 28 degrees. Now, why 28 degrees? There was an interesting paper which was published in Nature in 1984 from the center, which had a remarkable result, which showed that if you look at the cloudiness in the tropical atmosphere, it is a function of sea surface temperature. And in addition, it has a limit, it is a threshold above which the convection or the organized convection increases rapidly. And that's about 27.5 to 28 degrees centigrade. So this warm pool has a special place in tropical cloud formation like intertropical convergence zone and so on. So owing to this reason, the warm pool has a lot of interest in monsoon science. So what I'm showing you here is the picture of the warm pool. So all this shaded region is warm pool. It extends from the coast of Africa and Arabia, that's on the western side, across the entire Indian Ocean and into the Pacific up to about, say, this is about 140 west or something. So this is a large region where the ocean is pretty warm. So now large means the sea surface temperature is higher. So the storage of energy is very high. So when the energy is high, it has the potential to activate weather systems. Now, this region is called as warm pool. Now, if you look at closely inside this warm pool, there are some regions where the temperature is even higher. They are the maximum, and that's if you look at the month of April. Why April? April is pre-monsoon time, pre-monsoon month, when the tropical Indian Ocean is nearly the warmest. Right? At that time, the Indian Ocean warm pool is the hottest regions anywhere you can find in the world ocean. Now, within this warm pool, there are few regions. One of them is like the central part of the equatorial Indian Ocean. The other one is close to the Andaman Sea and parts of Bay of Bengal. And the third one is off the west coast of India, southern part of west coast of India. These regions are real hotspot. So one such regions where we had interest at that time, national interest and also for monsoon science, is this region to the west of India, which is called as the Arabian Sea mini warm pool. So this is one of the hotspots. So this is what we are going to, this problem is what we are going to look at using this ocean gender circulation model. Now, first we have to identify the problem, right? So here is how we can identify the problem. Now, ocean sea surface temperature is mainly determined by solar radiation. There are other factors, but the major factor is solar radiation. Now, solar radiation is a function of latitude and time, right? So, so if you just look at this first figure first, there are three boxes: one along the west coast of India in the middle, one in the Bay of Bengal, and one to the west of somewhere in the middle of the Arabian Sea, all along the same latitude. Had the sea surface temperature been governed by the solar radiation, all these regions, in all these regions, the sea surface temperature should evolve in more or less similar way. Does that happen? So that's what you see in this graph here. So the x-axis in this graph is months, starting from October, November, December, January, February, March, April, May, June. On the y-axis, you have sea surface temperature running from 27 to 31. So there are three graphs. One of them is the black curve, which is C. C stands for Southeastern Arabian Sea. That is this box. And this is a box to the west of it, and this is a box to the east of it. That is W box is blue, and eastern box is green. Okay. So now, if you look at this graph in the seas, the temperature there is higher compared to either of them, in spite of them being on the same latitude belt. That is the question. In spite of being on the same latitude belt, why does this region have higher temperature? Why does it attain highest temperatures during November, December, and so on, and compared to other regions? That's a question that we want to address. What processes control them? Now, why is it important? It's important because there is something called as monsoon onset vortex. So monsoon, the first spell of monsoon rainfall happens over Kerala. That happens on June 1st. So several studies suggested that associated with that onset, there is a vortex which forms in this region above the swamp hole. And here it is not very easy to identify them. They don't form very well every year, but they do form in certain years. So this is an example when it was formed in 1998. So this is a map of outgoing long wave radiation measured by satellites. When the satellites OLR is low, the cloudiness is larger. So in this region, there is a lot of cloudiness. And it is also associated with some kind of a vortex here. You can see some kind of cyclonic formation here. And that is sitting just above the warm pool. And that is why this warm pool, understanding the warm pool is important. Now, there has been some hypothesis about why forms. So one such hypothesis was that in this region, the salinity is low. Okay, this top left figure shows the salinity during the month of January. This is because If you remember this picture I showed you, the salinity in the Bay of Bengal is low, right? So the salinity in the Bay of Bengal is low because of all the fresh water coming here, and some piece of that low salinity water flows along the coast of India, around Sri Lanka, and goes and reaches here. And it is the same region where the worm pool forms. So there are some studies which propose that it is owing to this low salinity water that the worm pool forms there. So we have a hypothesis to test, right? And now, in order to test this hypothesis, the first thing that we need the model to do is to the model be able to reproduce the worm pool correctly, right? So that's what we check first. So we have the model set up according to this configuration, which I showed you in this slide here. And then we force this model and to see how the model is reproducing the worm pool. Now, this is at a location within that worm pool, 70.77 east and 7.14 north. And this is as a function of October to June. And this is a vertical axis, 0 to 120 meters. And these are contours of temperature. So this is the bottom panel based on observation, that is data, and the top one is based on model. So if you look at the shading, you will see a patch of very warm water, and that is simulated well by the model, just similar to the observations. In fact, the entire cycle from October to January is well captured by the model. There are two other curves here. One of them is the mixed layer depth, where where both temperature and salinity are uniform, and there's a blue curve where it shows where only temperature is uniform. So the difference between these two gives you the effect of salinity, and that is given as barrier layering. So the model also able to reproduce this thickness of the barrier layer. Of course, the small undulations are there in the model, which is not there in the data. So on the whole, the model is able to simulate the worm pool very, very well. So given that we can, because the model is able to reproduce it, we can use the model equations to understand what processes lead to the model worm pool. Now, these studies propose that the formation of the model of the worm pool is owing to the low salinity water. Associated with this also a circulation corner called as Lakshadweep Hive. So if you have to do that, then the model should also be able to reproduce the low salinity patches that you see. And evaluation of the capability of the model to reproduce the low salinity patch is seen in this figure. So here is the low salinity patch in the observations in the bottom panel and models in the top panel. It reproduces, although there is a little bit of shift when the maximum occurs. So this is owing to various shortcomings. So the theory, the proposal was that there is East India coastal current which brings low salinity water, which gets trapped here, which creates a barrier layer and which traps solar radiation and heats the ocean to very unusually warm levels. So the major challenge at that time was to get the low salinity water simulation right. So this was the major work gone into the model by to simulate the river runoff correctly. So you can see that the arrival of low salinity water into the Eastern Arabian Sea reproduced very well by this dark blue is low salinity water, which is reproduced very well by the model, so that the model is able to do that. Now, how do we test this hypothesis? So the hypothesis is that if there is low salinity water present, then you will have the water. So it can be done two different ways. First of all, what you can run the model without the river runoff or the rainwater, and then introduce the river runoff into it and see whether the worm pool forms or not. The other one is to make sure that you first get everything right, all natural, and then remove the process of low salinity water intrusion. So that's what is done here. And in order to do that, what is done is, because the model has some limitations in handling all these processes. So in one experiment, that is the control, you have the salinity varying as in nature with all the river runoff, fresh water and everything. And then you do another experiment in which the salinity doesn't change. That means it is held at a fixed value of 35 PSU everywhere in the model domain. The rain or river runoff doesn't dilute runoff anymore. So if the hypothesis is correct, the hypothesis that the warm pool forms because of the low salinity water, then we should not have the warm pool when the salinity is fixed, right? But the result we got was not consistent with that hypothesis. So that's what you see in this. Just look at this right-hand side 2 panels. The top one is the experiment where we have all the salinity changes, river, rainfall, and everything. And the bottom one is with the fixed salinity. So there was no change. The worm pool didn't care about the low salinity water. It is not responding to the low salinity water, which implied that the low salinity water was not required for the formation of the worm pool. So the previous hypothesis that existed was not right. And this is another representation of that. This is the evolution of seasonal evolution of sea surface temperature. The scale is to the left, and blue is when the salinity is fixed, and red is when the salinity is decreasing as per the seasonal cycle. So the sea surface temperature didn't have any significant response to these changes. So these experiments suggested that the low salinity water is not the real reason for the formation of the cold pool. So now we have another problem. Again, the problem is back to us. What causes the warm pool to form? So we looked at all the terms of the temperature equation, and in that temperature equation, we separated into various compartments, like SST is a tendency, that's the so-called del T by del T term, and then there is an atmospheric forcing coming from green, and all the vertical mixing coming from the red line, and horizontal processes coming from blue. So the blue and red are very small, whereas the tendency is mostly governed by the ASC fluxes. So that is what was given by this equation. So there is some processes happening because of the ASC fluxes. Now, if it is ASC fluxes, why it is different? Does it have a regional preference? Indeed, it has, and that is what is seen by this data. Okay, so this is the data that is going into the model. The first one is on the left-hand side, the net surface heat flux. Okay, and yeah.
Sir?
Yes.
Sorry to interrupt you. If there is ENSO, strong El Nino or La Nina, what will be the situation based on this hypothesis in the saline? What will be the effect on the salinity on this situation? Can you please explain?
Yeah, I will explain it, but let me complete this problem and then.
Okay.
Yeah.
Okay. Thank
Right.
you, sir.
Okay, so this is the data that is being forced. So the first one is net surface heat flux going into the model. And if you look at carefully, you can see that this heat flux region has a high. But if you look at in the northern region, it's more or less uniform. But here there is an isolated patch of high. Net heat flux is positive. And in all this blue region, there is loss of heat from the ocean surface to the atmosphere, whereas here it is gaining heat. And this gain in the heat is responsible for the formation of that unusual warm pool. And in order to supplement that, in order to amplify that effect, the winds here are too weak, right? If the winds are stronger, it would mix and cool the ocean. If the winds are stronger, it would make the evaporation higher, right? So this forcing is what is leading to the formation of the warm pool. Now, this automatically leads to another question, that why is this anomaly situated only over this region? And that is owing to the topography. Okay, let me go to the last slide now, so that it becomes very clear to you. Now, this is a picture of the topography, right? So this topography, wherever there is red, it is very high. What you see here is the Western Ghat mountain ranges, right? And during the northeast monsoon, what happens is that we have winds blowing from the land to the ocean. And in this region, because of the mountains, the winds are blocked, and on this side, the winds are weak. But when you go further up north, the mountains are not so tall, so the winds can pass through easily and cool the oceans. So owing to that process, in this region, the winds are weak. And that's very clearly seen in the satellite data where the winds are weaker here and the winds are strong on either side. So now, based on data, we have a new hypothesis that it is because of the weak winds and blocking of the winds by the mountains is the responsible for the formation of the pool. Now, how do we use an ocean model to test this hypothesis? Okay, so because we have the control over all the forcings, now we can replace this weak winds and with the stronger winds in the model and to see what the response of the ocean will be. So we carry out these additional experiments. One of them is called no Western Ghats winter, which means that winds, air temperature, and specific humidity over the southeastern Arabian Sea are replaced by mean value over Western box. That is this region, which is apparently unaffected by the mountains during the November period, November-February period when the whirlpool formation happens. Okay, so now what we're doing is we are killing the effect of the mountain and to see whether the warm pool forms or not. Now, this is the result from that experiment. So the black is a control one with all processes, and the blue is a previous one where we had the fixed salinity, and the red is mimicking the effect of the mountains. Now we have something interesting here. What this shows is that when the Western Ghats is not here, the winds would be stronger, and in that particular case, the temperature is much cooler. And the temperature is much cooler is suggesting that the warm pool doesn't form if the mountains are absent. So that is how we have been able to form. So this is an example of this. For example, this top one is the picture for the month of March when the control run, when all processes are present, and this is when the effect of Western Ghats is imposed. There is no formation of the warm pool similar to that of control one. So this kind of demonstrate that the effect of mountains are important for the formation of Arabian Sea mini warm pool. So the conclusion is that the formation of the mini warm pool in the Arabian Sea is due to the orographic effects of Sahyadris, that is Western Ghats, and salinity effects are not necessary for its formation. So this is an example of how we can use an ocean general circulation model which solves a complete set of equations to investigate the or to identify a process that is at work in nature. Now, it is not possible to do this cleanly with the data because when you do data, the data is done in real field and it has all the effects. Now, there was a question just now asked saying that what would happen in terms of an IOD year or an ENSO year or a monsoon year. So whenever this happens, we know that there will be some amount of variability. But that variability doesn't remove the entire process, but only either weakens it or strengthens it. For example, we know that the monsoon is a phenomena which happens every year. But sometimes we have a weak monsoon. Monsoon may be 10% less. It's only 10% less. So the water that is coming in there is 10% less. The salinity reduction may be 10% less, or the salinity may be 10% higher. So when all that happens, there can be variability from year to year. So using data alone, it is not possible to learn about the system. And in such circumstances, the model becomes very handy to look at this problem. So that's about the first example. So do you have any questions on this?
Yeah, I got my answer. Thank you, sir.
Any other question? Okay, fine. So let me go to the next example. The next example is on Indo-Ocean dipole mode. So this is an interannual phenomenon, right? It happens once in few years or so. Now, what is this phenomena? This phenomena it's a coupled ocean atmospheric phenomena, and its signatures include changes in sea surface temperature, cloudiness, and winds, and also the changes in ocean mixed layer and thermocline. So usually what happens is that the eastern side of the Indian Ocean is fairly warm. Eastern side, what I mean is to the east of India, so like something like 80 degrees to the eastern side. Okay, that's warmer compared to the western side. And the winds in generally are towards east. And also you have more rainfall and cloudiness on the eastern side. But in certain years, what happens is that the eastern side becomes cooler. That is shown by this schematically by this blue patch of shading. Okay, the eastern side becomes cooler, and that is more so to the coast on the to the west of this Sumatra and Indonesia and so on. At the same time, the western side becomes very warm. That's seen by this red patch. The western part of the equatorial Indian Ocean becomes warm. This is associated with winds changing its direction. Winds blow from the east to the west, which is a very unusual. Now, owing to all these processes, we have more cloudiness and rainfall on the western side and also over India. So, owing to these two signs of temperature, this is called dipole. This is the warm pole and this is the cold pole. So this is called dipole, and this is called Indian Ocean dipole mode. So this has occurred in many years, and the older years are listed here: 61, 63, 67, 72, 77, 82, 94, and 97. And recently we had a very strong IOD in 2019. We also had in 2016 and so on. So these events are occurring, and it affects the climate and weather of this region. So it is becoming important. So in this, for this example, I'm going to show you how we use this to study the Indian Ocean dipole of 2006, right? So this is a description of the IOD during 2006. In 2006, October, we had very cold sea surface anomalies on the eastern side of the Indian Ocean that went as much as 1.5 degrees. That's on the eastern side. At the same time, the western side was warmer. The SSTs are shown by shading. The western side was warmer. Okay. And then these contours show the anomalies in outgoing long wave radiation, OLRs. So the OLR was high here on the eastern side, and it was low here on the western side, which means there is more cloudiness on the side and rainfall, and whereas less cloudiness on rainfall on the eastern side. The wind, this is the wind anomalies. There were anomalous winds blowing from the eastern side to the western side. So this is a description of the phenomenon. So the first step we want to do, so we use an ocean general circulation model. It is the same model which I showed you before, and then it was forced by atmospheric forcing, that is ERI-15 reanalysis. And this was also used CMAP rainfall and SAGE river discharge. It also had a chlorophyll skating scheme. And then we used winds from QSCAT, and we did process transfer 2006. Okay. So this is the evolution of the anomalous winds during 2006. This was a kind of a special event because we had very strong wind anomalies in May, and also some kind of wind anomalies in April. In May, you can see that very strong wind anomalies blowing from east to the west. And those anomalies became weaker in June and July, but they picked up in September again, and October they were kind of strong. As in November they separated, and there was a patch of low winds at the equator, and it became weaker. So it is in October that we also show that the response to SSTs was very high. So that's the structure of the wind anomalies. Now, when we use an ocean model, what we want to see first is how good the model is. Is the model able to capture the phenomena in right magnitude, right time, and right location? So in 2006, we had a reasonably good satellite data set, which is coming from TMI, and that's what you see here. And these are all anomalies for 3 months of July, September, and October, right? And these are the two boxes which is traditionally used for calculating the so-called dipole mode index. So this is basically a normalized anomaly difference in anomalies between the eastern and western side. So there are two things to notice here. One of them is the evolution of this cold patch of SST. And the second is the maximum when the cold patches have persisted. So if you look at the evolution, you see that you see some signals of the cold SST patch happening in July. It becomes strengthening in September, and kind of reaching its peak by October. So this is in observations, and this is in models. The model does actually does a remarkable job in reproduce. So in my assessment, this is probably the best simulation of the Indian Ocean Dipole SST anomalies that's ever been made, as far as I know. So even when you look at the maximum, the spatial pattern of the IOD patches is very well reproduced by the model. I believe this is because of the exceptional quality of the winds and forcing that were used in this model. This is another way of looking at the capability of the model. This gives you the thesis for temperature. This gives an insight into the dynamics of it. And this is the sea level anomalies. So evolution of sea level anomalies in July, September, and October. So this is in models and October. So there are some differences, but on the whole, the model is able to reproduce these low sea level anomalies that is characteristic of the IOD in September and also in October, which is simulated, and the pattern of high sea level in the southern subtropical Indian Ocean, which is also reproduced by the model fairly well. Now this is the dipole mode index, and this is the difference. First, how we calculate the dipole mode index is we calculate the average anomalies between these two boxes, take the difference, and then normalize by the standard deviation. The standard deviation in the model is 0.42, and it's in the observations about 0.53. And then in the black is the TMI, the observed dipole mode index, and the red is the simulated dipole mode index for the period of 2000 to 2007. Even here, you can see that this climate phenomena, measured in terms of the index, is is reproduced by the model with a very high quality. Okay, what is this here? Yeah, this is the sea surface temperature anomalies. Now, one more measure of this model's capability is done here using the observed ocean currents. So at that time, there was a current meter mooring data in the central equatorial Indian Ocean as a part of the Rama project. And this here it is comparison of ocean currents. This is the top is the U component, and the bottom is the no, this is the U component. That the zonal currents are the strongest in the equatorial Indian Ocean. So the black curve is from the model, and the red is from the observations. And this is given for 4 depths: 50 meters, 100 meters, 150 meters, and 170 meters. Even the magnitude of the currents are simulated by the models are very good for a visual comparison. But you can see some differences. For example, here there is a departure at 100 meters between the model and observations. The observed currents are somewhat stronger by the model. But when you go to 150, it is not, the differences are not so large. So there are differences in some places, but the interannual variability and the seasonal cycle of the currents are reproduced very well by the model. Now, how do we understand the processes that lead to the formation of dipole using the model? So one way is to look at again the terms of the equation, and when we look at the terms of the equation, it is very clear that there are four curves here. First one of the model tendency, then the green is the atmospheric forcing, red is the vertical mixing, and blue is the horizontal processes. So the striking feature is the cooling that happens in the eastern box. So that's seen by this black curve, which shows a strong tendency in cooling, and that is basically initially it is triggered by a little bit by air sea fluxes, but it is mostly contributed by the vertical mixing that is happening as a result of the upwelling and vertical mixing, and then blue is a horizontal advection of this upwell water into the box that we are looking at. But when we look at the western box, even here there is initial contribution happening from the contribution by the vertical processes. But when we have the peak IOD event happening during the month of October, it is mostly contributed by the AC fluxes. So now, if you look at this curve, there are times when one process become important, and there are other times application in understanding. So we carried out a series of experiments. So what I would like you to learn is how the model can be used to isolate these processes. So here we can split. For example, we can split them. Because when we look at this curve, we see that at times the AC fluxes by the green curve is important, whereas other times when the blue curve, the horizontal advection is important. So one of them is a heat flux driven process. The other one is a dynamic driven process. So it requires that we need to separate them. So what is the role of ocean dynamics and what is the role of heat flux? So it can be diagnosed or identified by doing experiments by changing the dynamics in the model, which can be done by changing the wind stress, or you can change the heat fluxes. So now this is an interannual process. Interannual process, which means that the phenomena that is happening in one particular year has large departures from the climatology. So if we replace the data for the year when the IOD is high with a climatological data, the large departure is eliminated. So by replacing selected fields by the climatology, it is possible to identify the role of that particular process in generating the IOD-like pattern using the model. So six experiments are listed here. First one is role of ocean dynamics, and that's called a tau climb. And then what is done is climatological wind stress. Now, I must, at this point of time, I must also tell you that the winds appear in an ocean model in two ways. One of them is in the dynamical equation. That's for equations for U and V. There it appears as wind stress. Then it also appears in the calculation of sensible and latent heat flux, where it enters as wind speed. Okay, so so there are the two things. Now, to identify the role of ocean dynamics, we replace the winds with the climatological wind stress. And to identify the role of heat flux, we use wind stress for 2006, whereas all other parameters has climatology. This includes air temperature, humidity, wind speed, and everything. Then we can identify the role of winds alone. So there we keep both wind stress and wind speed as climatology, all others as climatology. Then similarly, we can identify the role of latent and sensible heat fluxes, and that is called LS climb and climatology of air temperature, humidity, and wind speed. And then we can also identify role of radiation by keeping the short-wave radiation as climatology. We can also identify the role of rainfall by keeping the climatology of rainfall. So these are 6 separate experiments. All these experiments are done for the year 2006 to identify what process lead to the formation of the IOD event. So this is a very simplified figure. If you go into the details, it is complicated. So there are different curves here. The black one is control, where we have all processes as in 2006, and then we have tau climb as red, where the wind stress is climatology, and then W climatology is in green, where the wind stress and wind speed as a climatology and everything. So each of them contribute a little bit. That's what you see in if you look at for the month of October, when the processes are important. So the control is here. So if we don't have, for example, the short wave climatology, these are actual SST. The SSCs are slightly cooler, right? On the other hand, if we don't have the wind stress, the SST would be actually slightly warmer. And among all this, the major contributor comes from winds. That is in terms of wind stress and wind stress climatology. And in addition, if you keep only the dynamical process, that has a significant impact. So this actually suggests that in the evolution of the 2006 dipole event, the important than the contribution of thermodynamics, the dynamics processes. Now, it is not the same for, this is for the eastern side, okay? This is SST eastern side, and this is for the western side. Western side is different, because one thing is that we have the warm pool there, the mixed layer is much deeper, there is absence of upwelling, and so on. So when we look at here, even here we find that the wind climatology is important. That's a run which reproduces the maximum temperature. But when you go to the month of October, we see that we have other processes are important. For example, blue here, heat fluxes are important here. And there is also contribution coming from latent and sensible heat fluxes. So the processes are different for the eastern and western side. Irrespective of that, what we see is that we can use an ocean general circulation model to identify which process is important in these processes. So one additional event that happens, additional episode that happens is the so-called intra-seasonal variations. So there are studies which suggest that these are intra-seasonal events contribute to a large extent into the evolution of these events. So we try to study this. There are these are the 3 curves. The black curve is the actual SST anomalies, and the blue is the intra-seasonal component, and the red is a slowly varying seasonal component. So here we see that it is the seasonal evolution component which is mainly contributing, with the intra-seasonal signals amplifying the signal to some extent. So it is even possible to understand the contribution of these intra-seasonal events by applying the appropriately modified forcing to the ocean general circulation model. So here is 2 examples. So the intra-seasonal has 2 major components here. One of them is the Madden-Julian oscillation, which mostly appears in the 30 to 90 day frequency band, and there are the sub-monthly forcing that appears in 10 to 30 days. So if you take the forcing field and then if you remove those variabilities, you get a different kind of winds for forcing the model. So one would have the intra-seasonal forcing and the other would not have the intra-seasonal forcing. And then we can apply the forcing and see how good, well, or what is the level, the extent up to which these frequencies are affecting the evolution of the phenomenon. So these are the results from that experiments. In one experiment, we don't have the submonthly forcing. In another experiment, we don't have the Madden-Gillier forcing. And in the third experiment, we have all the wind forcing. So here what we see that it is these anomalies are very similar. For example, if you look at the October, there is not much difference. So it is which suggests that this intraseasonal forcing is not very important for the evolution of the Indian dipole that happened during 2006. So in this event, irrespective of whether the MGO event is present or an MGO event is or the submonthly forcing is present, it reproduces. All that is requires is the slowly varying component of the wind stress. So interseasonal forcing is not very important, but it adds to the amplitude of it. Here is the sea surface temperature anomalies, SST anomalies, and there is intraseasonal anomalies. So it adds to the amplitude of it. So this is the summary of the result. The Indian Ocean dipole of 2006 is well simulated by an Indian Ocean model. And ocean dynamic processes had the dominant role on the cold SST anomalies in the east, whereas in the west, it is the air sea fluxes that led to the formation of warm SST anomalies. The Indian Ocean dipole evolves in the absence of interseasonal oscillations, but influences their magnitude. And yeah, there is another set of experiment which I haven't shown here. Is the thermocline preconditioning may be crucial for large amplitude iodic events. Thank you. So with that, I will conclude the lecture on applications of ocean general circulation models. And if you have any questions, I'll be happy to answer. Okay, I'm checking the chat box now. Yeah, I don't see any questions in the chat box. Is there any other questions? Are you able to hear me? I don't see any response. Can somebody respond? Are you able to hear me?
Yes, sir.
Yes, sir.
Okay, fine. Okay, is there any, if there are no other questions, then we can close this session. JS, you have any announcements? Okay, there's a question here. Can we attribute the frequent occurrence of IOD events in the recent past to the global warming, or are there any other reason? That's a good question. I don't think we have a clear answer to that question, because the first prominent IOD occurred in 1961, and then it more or less went unnoticed till the very large event in 94 and then 97 and so on. So there have been probably more occurrence of frequent IOD events in the recent past. So whether it is owing to the global warming, I do not know. Probably yes. It requires some more analysis to understand that. Because one of the problem here is that we still do not know how what leads to the formation of Indian Ocean dipole. Is it originating from the ocean, or it's originating from the atmosphere, or is it just positive feedback happening? That's not very clear. So only when we understand that, we will be able to address this question. So this is a kind of open problem. Why we have IODs, and why do we have them in global scenario? But given that, I would consider that the upwelling that happens near the coast of Indonesia is very important in determining the strength of the Indian Ocean dipole, because the cooling there is a major driver. And whether the winds have changed, whether it's a local amplification of the upwelling, those results are not learned. Probably it is possible to check those things using the large data set that has been released from the latest climate experiments, various scenarios, and check them. Yeah, that's my comment on that. To Sumit Mukherjee. Thanks for the question. All right, then, if there are no other questions, let's close this session. Thank you.